Thank you. Good afternoon, everyone. Welcome to the Energy Dialogue on how to operate and build reliable power systems into the future. This is our second Energy Dialogue in our series of dialogue. And this particular dialogue is really has been framed as a training webinar or a capacity building webinar. And the aim for this dialogue is that as we really see a transition into, greener or cleaner, more energy technology systems that are variable, such as, solar or wind in itself, it provides, right, the energy transition in itself provides opportunities, but it can provide some challenges for system operators who are really just used to operating more stable forms of energy. So the aim of this dialogue is to really unpack, I guess it's been framed as a Power Systems 101, is to really capacitate the stakeholders in attendance today in terms of, what power systems is, as well as how the grid can, and the terminologies, and provide just a really good understanding as we move into the more technical discussions that will be taking place next week. So that's the aim of the discussion, and I'd really just like to welcome everyone, as well as mention the PCC commissioners who are in attendance. And so what's also really important to note is that this is a collaboration with the PCC, UCT, Eskom, as well as the Australian High Commission. And just to link this particular dialogue to the work that we are doing as the PCC, when we made recommendations about earlier this year about electricity, we really recommended quite an increased number of variable renewable energy within the South African grid. And sometimes stakeholders often question us on whether or not the grid would be able to manage such increased volumes of variable renewable energy. And that's why we have really, decided to partner with UCT in terms of understanding, grid operations and systems balancing in this knowledge exchange that will include both local and international system and grid operators. And with that, I'm going to hand over to Jessie Burton from UCT. So she will really lead and facilitate the discussion. And over to you, Jessie.
Thanks so much, Simpiwe. Good afternoon, everyone. So my name is Jessie Burton. I'm a senior researcher in something called the Energy Systems Research Group at the University of Cape Town. Just to follow on from what Simpiwe was saying, the PCC has also had some previous webinars covering also some introductions to some of the concepts that will be introduced today. So if you're interested in that, you can go back and have a look. There was one called Balancing the Electricity System and one on electricity system reliability and sustainability. And we're moving on from the content in those today. So we have two amazing speakers. I'm so excited to introduce them. David Oyedokin holds a PhD in electrical engineering from the University of Cape Town. He completed his postdoc study at SANSA, the South African National Space Agency, before he joined the Department of Electrical Engineering at UCT, where he's currently an associate professor. David's research interests are in renewable energy, power system stability, and geomagnetically induced currents. And he's an active member of the Power Systems Research Group at UCT. They're in ElecEng, we're the Energy Systems Research Group, we're in ChemEng, but we're working together on this project. David is the recipient of the IEEE MGA Gold Award and the EBE's Faculty Special Award for Social Responsiveness at UCT. And he's a past chairman of IEEE South Africa. Over the years, he served in many IEEE committees and organizational units and has led several EPICs and IEEE and TISP projects in South Africa. So he's going to kick us off with a more theoretical and conceptual introduction, and then we're going to have Keith Bowen. Keith's the senior manager for market operator in the Eskom transmission division. Keith's responsible for developing wholesale pricing mechanisms, supporting internal transfers within the vertically integrated utility, and payments to IPPs. With the restructuring of Eskom, he's involved in developing future market mechanisms and trading arrangements between the transmission subsidiary and other industry participants. And Keith has a master's in economics from WITS. So Keith will then go on from the content that David will talk us through into a little bit more of the real world questions around planning. So with that, I'm going to hand it over to David to kick us off. Thanks so much.
Thanks, Jesse, for that introduction. Good day to you, and thank you for joining us this afternoon. I'll be taking us through a few slides on fundamentals of power systems, where we shall look at concepts around voltage, current, power system frequency, inertia. We'll delve into the generation mix, converter and interface generation, issues around variability in renewable energy availability. We'll talk about, in brief, the stability of the electrical power system, and then we shall look into reliability and power quality, and that is where we'll park the presentation for today. So Jesse mentioned a lot about my research interests, so it's my pleasure to just go through this slide and just remind us within the context of the webinar today that electrical voltage is generally defined as an electromotive force. Some people call it the pressure between two electrical points in a closed electrical loop governed by Ohm's law. Then that pressure or electromotive force allows the flow of electrical current through a conducting material. In this case, it will be, as an example, electrical wires within the power system. And that links to our definition of electrical power as the rate at which electrical energy is consumed. And one of the fundamental reasons why we have a power system is to ensure that we have electrical power to meet the load demand. And within that context, we have what I'll call the generalized view of a complex system, an example of which is the electrical power system. It has a number of key elements such as scope. In the case of the power system, it is put in place to ensure that power is available to meet the load demand, but most importantly, in a reliable and sustainable way. It has many components. Would say it is an assemble of components that are interconnected. And what's quite interesting about this is that these components are mutually interdependent. That notwithstanding, each component has specific roles that they would play within the power system to ensure that the power system has elements of being permeant, that is, it's expected to exist for an indefinite period of time. But in practical sense, each component will have a lifetime, and the idea is to embark on a reliable process through which power system components are being maintained. Speaking about an ensemble of components, we have the generation side of things. The non-renewable will be coal as an example. From the renewable energy side, we would have solar PV, biomass, wind. And within this context, we have the transmission infrastructure as well as the distribution infrastructure that are put in place to ensure that available power reaches load demand in a safe and reliable way. In addition to this, we have various protection schemes in the network that are there to ensure that we have a power system and operate it in a reliable and safe way. And there are generally two horizons that we talk about, which is the planning horizon and the operations time horizon. Planning horizon, usually 5, 10, 15 years, depending on the utility. But operation horizon, we're talking about what happens now, the next minutes, the next 5 minutes. That's the two horizons that needs to be catered for extensively when we talk about power systems and their operations in general. Putting this into a model, we have our traditional power system without renewable energy resources. This is a modified multi-machine power system that would have, as an example, 4 large synchronous generators. These are G1, 2, 3, and 4 in the right-hand side of this slide. And what we see here is these generators coming together, well synchronized in the grid. We're not going to go into the technical details of synchronization, but the idea here is that they work together in concert to ensure that power gets to the load, which we see the green rectangles at the bottom, in a reliable and a safe way, such that things like the grid code and operational requirements are met well. Within the context of the evolving power system, where, as an example, in the South African case, we have an increasing number of wind farms, solar PV, and CSP coming together within the generation mix to ensure that power is available to meet demand, but most importantly, in a sustainable way, relying a lot more on renewable energy resources as compared to where we're coming from, which is a higher reliance on non-renewable energy resources. These changing generation mix brings about a number of complexities, but those complexities provide opportunities which we have embraced and will continue to embrace moving into the future. Some of us may have heard about, as an example, the saturation of the Northern Cape with PV installations with respect to the ability to evacuate that power from the Northern Cape. Our colleagues at ESCOM will be able to speak more about that in fine details. In this model here, we have an 80-kilometer line that just shows you how power will be transmitted from one area of the network to the other. And we don't have an unlimited amount of transmission infrastructure. There are constraints such as thermal limits that require adequate planning for in the short and medium-term horizons. Within that context, you may have heard about power system frequency. What we know for sure is that frequency within the context of power system is a parameter that has no physical existence. It's, of course, the property of electrical current and voltage, and it does represent something that can be measured. In this case, the rotation of our electrical machines. And in general definition, we talk about the number of cycles in 1 second, and the unit is in hertz. Within the context of power systems, frequency in general also gives us an indication of how well load and generation is balanced. And this is one of the critical elements in the discourse around renewable energy penetration in our power system. How do we balance load and generation? Knowing fully well that these are not static parameters. Turning off the light switch in my office or shutting down a building in a complex corresponds to a reduction in load. Somewhere down the line, a generator should be reducing the amount of power produced because there's no load to consume that. So there is a continuous balance between demand and generation, which is one of the key elements of power system control. Within the context of renewable energy systems, in the coming slides, we shall expand on this in a bit more detail. There is another concept within power systems, discussing about the fundamental of power systems within this evolving power system structure, is the idea of power system stability. It's based on a few fundamentals. And the first is, we'd like to keep the lights on, would like to keep them bright enough, so not half light in inverted commas, as you may have heard. Would like to keep them steady without flickers, and would like to ride through contingencies as much as possible. And within the IEEE task force on power system stability, we have a well-established definition, which I have on the slide verbatim, because it is the definition that has been accepted in the space globally. And we define power system stability as the ability of an electric power system, in the context of South Africa, the main transmission system, and down to distribution, for a given initial operating condition to regain a state of operating equilibrium after being subjected to physical disturbance, with most variables bounded so that practically the entire system remains intact. And I think this definition contains a number of critical elements. And the first is a given initial operating condition, which we'll define as a steady voltage and expected level of power quality, which we shall discuss. That's a state of equilibrium. It is not 100% balanced. If you've been to control centers around the country, you see the frequency fluctuating, but within the bounds allowed for by the grid code. Similarly, if you put a multimeter at one of your 230-volt supply points at your home, office, wherever you are, you would see that there is a slight variation. But again, that is within the bounds, ideally, within the bounds of what the grid code allows the power system to be operated in. We talk about disturbance, we refer to a sudden loss of load or generation. Fault could include vehicle accidents against municipal infrastructure, leading to a short circuit in a power infrastructure going off. It could be fault at our power stations, a factory shutting down for the weekend. These are all contingencies that affect the balance of power demand and generation within the power system that has to be managed adequately. In recent years, the definition of power system stability was expanded to include converter-driven stability, resonance stability, and this is to ensure that we respond to the increasing number of renewable energy-based power generation in utilities across the world. And due to the decreasing grid inertia resulting from the displacement of synchronous generators, we have this possibility of frequency excursions, that is, this change in frequency that can become faster and increase the likelihood of instability. So these are some of the challenges that we have. That notwithstanding, converter interface generators have the inherent ability to respond a lot faster, than some of our conventional coal-fired power stations. So whilst these challenges are there, they come with opportunities, and working together, we will be able to address some of these challenges. We have, utilities across the world that have very level of renewable energy penetration, and there are lessons that can be learned as South Africa, forges ahead with this Just Energy Transition Program. When there's an event in the power system, one of the I usually like identifying what is the root cause and then the next reaction to it. So that there will be a reaction to an action. So let us assume that the action is we lose one unit at one of our generating stations. At that instant in time, the next millisecond, what happens is that we have the load slightly higher than generation, and that typically drops the frequency. So figure 3 here depicts 3 distinct periods during an event that causes a decline in frequency. And this is for a system that is dominated by synchronous generators, like we have in South Africa at the moment. And the primary responsibility of primary, secondary, and tertiary frequency control is to restore this. The discussion around a reduction in system inertia is linked to the fact that we will have a reduced number of synchronous machines if we increase the penetration level, keeping all other conditions constant. Synchronous machines have, as part of their inherent characteristics, inertia that helps to rapidly provide power or reduce power generation based on the changes in the load. But for these part here, converter interface generation-based generators are able to provide some of that, but of course within constraints. Looking at variability in renewable energy availability, we have a simple profile here. Just to provide a basic analogy, within the context, we have a load profile, which is in red, and of course we have generation, in this case solar. We have the traditional bell shape where the peak in solar generation coincides with around about midday. It is extremely low to nothing in the morning, and late in the evening it is not available. But what we have is there is a certain level of load that is always on the network. So the question is, when we don't have solar power generation, how would we manage meeting the load demand? The answers are there. We have alternative generation sources. We may have a bit of wind power in the network. We can utilize battery energy storage systems to show up that reserve, and we can have some of the existing non-renewable energy sources, such as the coal-fired power stations, to help out with some of those windows. So those are some of the challenges that comes with operating the power system at an elementary level with solutions towards meeting those challenges. Another concept that I'd like to take us through this during this webinar is the idea of power quality. And just generally putting it, we talk about the measure of electrical current and voltage relative to ideal and expected conditions. We have cases where we have high voltage levels, under voltage spike and variations, voltage dips and sags, harmonic distortions, and most of these, in essence, are not what we want. And the grid code stipulates the maximum number of level of harmonic distortion that is allowed to exist in the network at various measurement points, the lowest dip that should be realized in the network in the event of a contingency. But what leads to power quality issues in general are matters regarding overload, especially at far-flung ends of the network, insufficient reactive power support protection malfunctioning. And the impact that we have seen and know is that we could have grid and consumer equipment damage, which of course is not the operating space that anyone would want to operate in. Is our power system reliable or not? Well, at the moment, we have two aspects of power system reliability, which I will talk about in brief. The general definition is that within the context of power system reliability, we want a power system that is able to perform its intended function in a reliable manner. That is what we expect. But there are two concepts linked to this. And the first is adequacy, which speaks to one question. Can we supply the load demand? And the second question is, can we do this while satisfying operational requirements, such as the quality of supply, the frequency drift bounds, the voltage range that is, put down by the grid code. So that in its entirety speaks to adequacy within the context of power system reliability. Then when we talk about security, we're speaking about the ability of the power system to withstand a predetermined set of disturbances. This could be the loss of a generating unit. It could be the switching on or off of a major load. And it could be a combination of this in some form of multiplex arrangements. System adequacy, speaks to the ability of the power system to have the necessary resources to convert primary fuels into electricity and then transfer it to the end user in a reliable manner, conversion from primary fuels, from the coal silos all the way into the generator, down into the power transmission network, down into distribution. Then from the generation side, do we have enough generating import capacity within the context of a dynamic power mix with renewable and non-renewable energy resources? From a planning and operational perspective, it is important to ensure that generation adequacy is met through this power mix that will be changing as the various penetration levels of the different renewable energy resources begin to grow within the power system. In a similar context, is applied to network adequacy, speaking about the transmission infrastructure, distribution, and cross-border interconnections. In our context of the South African space, we have interconnections with the Southern African Power Pool, Namibia, Zimbabwe, and the rest of the countries within the SAPP, that's the Southern African Power Pool. And then Keith, our colleague with markets, is more positioned to to speak about market adequacy? Do we have the right framework and tools to ensure that we can trade and allow power to be available on demand, still ensuring a high level of renewable energy penetration within the network? Then, as we wrap up our presentation, I'd like to highlight power system security. And this is quite an important aspect because it interacts with the markets and investor confidence as well within the context of power system reliability. In the short term, we are concerned about access to primary fuels, system adequacy, the market elements. And then in the long term, in the short term, if there are certain disturbances, i.e. the loss of a generation unit, is the power system able to respond to that whilst keeping the lights on? Within the grid code, there are elements of reserve spinning capacity that is there to ensure that within a reasonable set and number of contingencies, we can still keep the lights on. So these are elements that are increasingly important as we consider a power mix that is more reflective of the just energy transition program that we have, and also just reducing the level of carbon emissions that comes from power generation in the country. National Grid UK has quite a number of interesting data sets coming out online. And I decided to bring some of this into the presentation just to show us that, as an example, on the day this data was collected yesterday, they had about 30% penetration of renewable energy. So we can sort of see what is happening elsewhere in the country, elsewhere in the world. Then looking at the details of that day, at the bottom right side of the screen, you have access to the various profiles of the generation type against the load. And you can begin to see that it is a dynamic space, but within the power system operation, there are resources available to manage this quite effectively. What is interesting here is over the period of over a 10-year period, looking at the bottom right graph, what is clear is that the coal generation has dropped from about 16 gigawatt down to just under 2 gigawatt. And then we can clearly see an increase in wind power generation in green, as well as a steady increase in solar power generation. So these are some of the elements that are important in our discussion on and around the power system, the fundamental concepts, introduction to the issue around renewable energy and reliability, and how all of these can be put together to ensure that we reach the objectives that the country has set. There are challenges in modern power systems which have highlighted the role of power electronics, imbalance, harmonics, transmission, distribution, thermal limits, based on the fact that we have embedded generation at various levels of the network. And these provide opportunities which UCT as an institution has responded to. We have 2 patents in the space and a number of R&D projects, as well as research initiatives to address these challenges. I would like to acknowledge the contribution of colleagues from the Department of Electrical Engineering, some of our postgraduate students, and our academic material and data from National Grid UK that has contributed to the material that I put together for this presentation. Thank you, JC.
Thank you, Prof. That was amazing. It was very comprehensive. And I just want to say to everyone, please feel free to ask questions. We can collect them in the chat, or you can put it in the Q&A, and we'll come back after Keith's input and have a little bit more of a discussion. I think if I can just summarize and tell me if it's wrong, that was really comprehensive. I think it's very helpful. My key takeaways are the reason we have a power system is to keep everything in balance. And a reliable system does that. It does what it's supposed to do, which is meet demand with quality power in light of possible disruptions. And it does this at every moment, and we have to plan in every moment and for many years into the future. And that's really like the challenge of this integrated system. And the integrated system has generation and network and demand as part of it. Is that a good summary?
Absolutely.
So thank you for that. Please, to all of our attendees, put questions in. Don't be afraid. There are no stupid questions here. If you want to know what was ACG, what does synchronous mean, is load the same word as demand, don't feel embarrassed. Put those in the questions, and we've got people here to answer those questions. I see a hand. Louise, do you want to come in quickly before we move on to Keith?
Good afternoon, everybody. I want to know, are there like people sitting there minute by minute having to do this, do that?
Should I? Yeah. So, Louis, great question. I don't know if it's a sad answer, but the real answer is yes. We have our power system control centers. I've been into a few of them across the country. They are manned 24/7 round the clock. They require special skills, extreme level of intellect, patience, and diligence. They've gone through an extensive level of training to, without panic, ensure that our lights stay on. Most of the operation is automated, but from time to time, they require human intervention. I hope that answers your question, Louise.
Thanks. Thank you so much. There's one question in the Q&A that I want to take before we go on to Keith, because I think it's very critical for the kind of understanding. Can you explain again, please, David, in those seconds where we lose a large unit and we want to keep stability going in the power system, what happens? I think you had a really nice slide which showed the primary response. Can you quickly go through that a little bit? Let's take an example. Suddenly a huge unit, one of the biggest units on the system, like a Coburg unit, trips. What happens?
All right. Thanks, JC. So I think this is the slide you made reference to. So just painting an example, I don't hope it happens, but let's assume we lose Coburg unit 1. It's about 900 megawatts. That's a lot of power. At that instant, and it's located in the Western Cape, we have massive generators around the country, especially in the coal belt, with power import and export through 765 kV line between the various parts of the network. At that instant, which is here, what will happen is, and I haven't explained the concept of local frequency instability, but just to make it simple, at that instant, the net power generation in the network has reduced by 900 megawatt, but the load practically stays the same. So at that instant, we will see a slight reduction in frequency, but the network control will ensure that the rest of the generators are available to mitigate that by increasing their generation instantly, well, in practical sense, within a few milliseconds or seconds, to ensure that that deficit is met. If we don't have that reserve capacity to meet that deficit 900 megawatt, the network will go through a load shedding or load reduction process to ensure that since we don't have generation, we'll have to drop some load to ensure that that balance between generation and load is kept at all times. The next phases speaks to various elements of frequency control from primary, secondary to tertiary across various time windows to ensure that the frequency or the balance between generation and load is met. Now, just many years ago, say 20 years ago, we had contingencies in the network, loss of units, etc. But at that time, there was sufficient power reserve to ensure that without load shedding, the network can crank up generation to meet the generation deficit. I hope that helps, JC.
That's very helpful. Thanks, Prof. So I see lots of questions. I think some of them are also going to be answered a little bit in the next input. So let's move to Keith. Let Keith talk us through the kind of different kinds of planning processes, and then we'll come back and have a discussion together to answer all of them. Thanks, Keith.
Great. Thanks very much, Jessie, and afternoon, everyone. I think for this presentation follows very well after what David has already dealt with in his presentation, specifically on the theme of the interconnectedness of the power system. The Economist a couple of months ago published a very interesting article about the nature of the power system and how it really is one of the most complicated and sophisticated human machines on the planet, because there are so many moving parts, so many components that need to always work together to ensure that the system meets the demands of the participants or the consumers. I think one of the important things is that, particularly if you consider the size of an interconnected system going across an entire continent, so much work has to go into the planning and the operation of that system. And it just means that a lot of the engineering that David has talked about in terms of how we plan for these things and the technical capability also needs to be coupled with some of the economics of it. And what is the most cost-efficient way of trying to execute on this delivery, and how do we make those decisions over time? So what I would like to spend some time on is talking about those components. How do we do the planning, looking at those different planning horizons, and what it means in terms of the operation. So obviously, one of the building blocks for this is generation capability. And when I talk about generation capability, obviously I'm going to talk about the supply side generation, but it can also apply to demand response capability, that you have some demand response that is able to respond in the same way that a generator does or in a similar way. But here we want to just focus a little bit on those characteristics. And I think importantly is understanding that different generators have very different technical characteristics, but also then lead to different economic outcomes. Specifically, if we look at fixed cost versus variable cost. And here, in the traditional world, we would have looked at nuclear, coal, diesel before 15, 20 years ago, and including pump storage to some extent in that, is how we made decisions was really based on those different dynamics about what was the fixed cost of a generator versus the variable cost. Obviously, by definition, when we talk about the fixed costs, is that you build something, there's a lot of capital expenditure, there might even be fixed operating costs associated with it, but it means that no matter what the output is of that generator, the cost is constant. It is a regular cost that has to be borne by the owner, and only once you actually start generating, you start then getting into the variable cost component of it. And that means that if, for example, if we build, as we have done, lots of diesel generators, the diesel, the open cycle gas turbine is one of the cheapest forms of generation. It's quick and easy to build relatively compared to coal and nuclear. So you might build more of it as a backup, but then the actual operating of it is incredibly expensive. Whereas a baseload coal or a nuclear in the traditional sense would have been something that provided a huge amount of cheaper energy over a longer period of time, and therefore you would have a combination of those things in the past. And that's pretty important when you look at how we design into the future. Even before 15 years ago, while coal might have been the cheapest solution, particularly for South Africa, and you look at, oh, we're going to build lots of coal, and we did, it wasn't the only source of generation. Because again, you can build for 100% reliability, you can build it all coal, but then you have to deal with the reality is that one, it's not particularly flexible, but two, it's also that you may be overbuilding, and we did that too. But the issue is then you've actually built capacity that is underutilized. So even a coal plant at a 20% or a 30% load factor is ludicrously expensive, whereas building a few diesel generators, or as we did pump storage, there's a sunk cost, there is a fixed cost associated with it, but it's there as the backup, and it can meet maybe 5% or 10% of the demand, depending on what is required, and instead of building an entire new coal power station to be underutilized. So that combination of the choices available is such a huge component of the forward planning for a new system. Once we add gas into the mix, and of course historically in South Africa there was always an issue in terms of the shortage of gas, but globally gas is a big game changer in terms of providing flexibility and more recently being competitive with coal. But the dynamics of gas are similar to diesel, but not to the same extent. Whereas for renewables, we're now looking at a technology that is all about the sunk costs and almost nothing in terms of a variable cost. So once we have sunk and built that renewable generator, you really want to maximize its output. You very limited capability to adjust. And even if you did, there is an economic cost to that. There's a lost opportunity that comes with curtailing renewables. And I know we get a lot of arguments about how, in South African context, we've got the renewable IPP program, and from an Eskom perspective, we have to run them because we have to make them whole through deemed payments, etc. But even if those weren't private generators, it would be the same for Eskom if the Eskom were the owner or any other generator. Reducing its output has a true economic cost, and someone has to be paid for that. Either it's the owner or the off-taker or somebody. It's basically generation that's being thrown away. So it's an important aspect when you consider the technical capability and needs of different generators to bear that in mind when we look into what do we build and what are the consequences if we build that. In terms of time horizons, I think it's quite important for us to have a good sense of what that planning horizon is. So as David identified, in the future, we look at sort of far into the future, 10, 15, even 20 years ahead, looking at what we need to build. And the big reason for that is, one, long lead times. So if we're looking at the traditional building of coal and nuclear and other, and even pump storage, there's a long lead time required for that. So you have to make the decisions huge, long distance in advance. As we get to more and more flexible generation, so then that decision-making sort of window is a little bit more, is sort of closer to real time. But it does mean that when we look at that, almost everything is variable. We decide on what we're going to build, where we're going to build it. There's a lot of choices that are made available. But as we get closer and closer to real time, you move out of the realm of full variable costs to having a lot of your costs now being fixed. And so therefore, when we move into maybe a 3 or a 5 year window, and you start looking at the fuel supply, so you've got a coal power station or a gas generator, you need to make sure that you've built in the contractual requirements for that coal supply or that gas supply. And that then means that you start limiting your options even further. From the outset, obviously positioning the coal plant would be very much dependent on where the coal supply would be coming from, and similarly with the gas. But once you've positioned it, then it's a matter of trying to ensure that the investment takes place in those fuel sources and keeping up to date with that and those decisions. Sometimes it means that you would have bound yourself as the developer into a contract that is now not necessarily the most economic. It was in the sort of longer term view, but as dynamics have changed in the market in which you're in, and the supply and demand mix around you, it means that you do become more tied. So you might have a minimum offtake requirement, or even a maximum that you can go to without going to the spot market, which might be at a completely different price. There is that risk that, as we're moving out of that window of the 10, 15 years ahead towards 3 years ahead, or even a year ahead, your options become more limited. And then we talk about the day ahead. And I'm going to spend a bit of time on day ahead in real time, because that becomes quite crucial to how we operate the system. Even then, almost everything becomes fixed to a large extent. You have the short-run marginal cost, and short-run marginal cost then becomes the key decider for what gets scheduled and dispatched the following day, obviously within technical parameters. And that means that some of our costs have become fixed over that time. Obviously, the investment costs, the fixed O&M, all those kind of components, and going down to even the fuel cost to a large extent becomes fixed, because you have minimum burn and maximum burn that is applicable for that particular day of operation. I can remember in a time in Eskom, and it shows my gray hair, where the burn plan was everything. If you planned for the use of coal over a certain period at certain power stations, it didn't matter what the conditions were at the time, you had to meet the burn plan. The burn plan came with a capital B, capital P, and you could not deviate from it because the economics of the burn plan was decided a year, 2, 3 years in advance, and it had to be met. And that kind of then indicates that a lot of the time your decision making gets limited as you get closer and closer into the real time. So when we look at maintenance scheduling and a lot of the production planning, you really do look at a year, 2, 3 years in advance, because you have to, particularly from a system operator perspective, ensure from a maintenance perspective, you're coordinating outages to ensure maximum availability, or at least the best availability you can get at any particular point in time. Then in the day ahead, we then focus at unit commitment. Now, the question can be, so what's so important about the day ahead? And a lot of that is around the flexibility of the generators. If we're dealing with, as we have historically, large coal power stations, decisions have to be made almost day ahead to determine which generator will be running, if you have a choice, and at what level. You'd have to make that unit commitment decision a day in advance. And sometimes it even has to be a week in advance, depending on the flexibility of the unit. But generally speaking, we tend to kind of peg it at a day in advance. After that, you can make changes in terms of the dispatch, but whether the unit is running or not, and assuming the availability stays as suggested, it really is, again, your hands become more tied because the unit is there. Now, what do we run at the most optimal level? Obviously, some generators have a lot more flexibility, whether it be gas, pump storage, diesel generators, batteries. Those then become with a little bit more flexibility. Unit commitment doesn't have to be done day ahead, but it's still part of the optimization looks at that in conjunction with your less flexible generators to make sure you're optimizing the system as a whole. And then as we get closer into the real time, we then have to deal with how we dispatch and deal with the issues that David was highlighting when we deal with deviations and variations from what we had expected. On the day ahead, as I mentioned, dispatch or scheduling is usually done on the short-run marginal cost. So what we would do is you kind of build up a sort of merit order in terms of the short-run marginal cost. All the other cost elements have now sort of gone out the window. You're not worrying about what is the cost of the next generator, etc. That's done. We're only focusing on the day ahead. What is the cost to operate in the short run, each of the generators, and you stack those. Even then, when you're going from hour to hour, there are constraints that happen. So generators, particularly large coal power stations, even nuclear power stations, they have ramping capability. So they cannot go from 100 megawatts to 500 megawatts in the matter of 10 minutes. Those things take time. So even when you make a decision about a specific hour, it has ramifications on the hour before and the hour after. So day ahead kind of optimization really works at a minimum, looking at least cost over the 24 hours. So you look at the possibility that you might run a more expensive generator in 1 hour because it's more flexible. You then have both generators available over the peak at their maximum. So that kind of co-optimization over different windows has to take place on a day-ahead basis. And what we're always doing is making sure that you schedule against your demand. So in this graph, you can see when we look at marginal costs, if we stack them all up in the merit order, you essentially get the supply curve for the industry. You'll see that the supply curve doesn't start at zero. And that's mainly because we have these minimum generation points. If you're dealing with large coal power stations like we do at Eskom, there's a point at which you're never going to schedule a generator below its minimum stable generation point. Often that's about 60% of the maximum rating, sometimes more, sometimes less. But that is where you would schedule to start from. So if you're planning for tomorrow and you've got a peak and you're optimizing over the whole 24 hours, you will find that there will be some good 6 to 8 hours between 10 o'clock at night and 6 o'clock in the morning where you might be running generators at their minimum, because taking them off is not really a feasible option, and they can't run above that point because it's just too expensive. So they would run through the night at their minimum. So what happens that if all of them are at their minimum, you start having a bit of a technical constraint because now you don't have any capability of going down. And we have that problem, and we'll talk about it shortly when, for example, more wind comes onto the grid or it's generating than what we had anticipated. And now all the generators are sitting at min-gen. We then have what we call the dump energy problem, where you actually now have to curtail the wind because taking a generator off on the other side really is not a practical option. So then if we start at that point, You then have the prices or the costs sort of escalating over the window. And as I said, in each hour, that curve might be completely different from 1 hour to the next based on the technical parameters, what's available, what's the ramping constraints, those sort of things which might impact. So you may find that there are some generators that are available over the peak, but they're not available at 3 o'clock in the morning. And it might be, for example, our hydro facilities. So at Geriepe and Van der Kloof, there's a limited amount of water. You may then make sure that that water is available for the peak and not available for other periods of the day. That then has an impact on your supply curve. And that intersection then really becomes your schedule of what we say we're going to do tomorrow. What happens in real time then is a completely different thing. And David went through this pretty well. So I'm going to try and summarize. Obviously, in South Africa, our frequency target is 50 hertz. Between 49.85 and 50.15, we sort of have a dead band where we allow that the frequency can shift and drift, and it does. And we're not going to try and tightly control it as we might have done historically. What we use to control that movement of the frequency is regulation, or the secondary reserve, which is really automated generator control. Regulating control really is there to send out pulses from the central system operator system to various generators to get them to back up or back off, depending on where we are on the frequency. So the frequency curve can go above or below 50, and you're trying to manage it within a certain bound. That regulation control, also you try and spread it out amongst a large number of generators, so that you're not relying on 3 or 4 generators to provide that regulating capability, and then find they're not there when you need them, or you have a limited capability because one of them has tripped. So the idea is to try and you certify a whole lot of generators to be able to provide that capability. So it might be 40 to 50 megawatts per generator, and you want 500 or 600 megawatts. So you're trying to get 10 or 12 generators provided. The other benefit of that is that it gives you more movement, faster movement. So because each generator has a ramp, if you send a signal to 10 generators, you get 10 times the ramp effectively. So you're kind of able to move up and down a little bit faster on the regulating reserve. That primary reserve that David mentioned, which is this instantaneous reserve, is when things go outside that window. Normally it triggers about 49.7 on the downside. If you pick up that you've dropped below that, as mentioned, David did mention that there's a relay at each of the power stations, and it can be at a large number of customers, particularly big smelters, where they can actually interrupt. So for the customers, they see the relay, it triggers a response. It doesn't have to be indicated by a central system. They just see the relay. They know I have to respond to this event. And so therefore they withdraw demand, maybe for 10 seconds. And it's just enough to actually arrest the drop and bring back and allow for regulating in 10 minutes and other reserves to kick in to be able to bring the system back into balance. That instantaneous reserve, again, you spread that over as many generators and customers as you can get, because you need quite a quick response. As indicated, as we lose inertia in the system and we're getting a faster response to a drop, so a Coburg 900 megawatt will have a higher rate of response now than it might have had 10 years ago. And in 10 years' time, probably even have a higher rate of response, because there is limited inertia in the system. You need to have a lot more instantaneous reserve there to be able to pick up and deal with the system. Obviously, we're looking at such things like very fast response, or which then allows for even microsecond kind of response to be able to arrest that frequency decline. So that instantaneous reserve, which is what the phrase we use in South African grid code, is essentially the primary reserve. Then we have the regulating, as I said, which is generally there for managing the load following and trying to keep the frequency within the band. But it also, obviously, when there's an incident, it will kick in a little bit later than the instantaneous, but the pulses will be coming from the central system to get the generators and other suppliers to pick up. Then a little bit later, the 10-minute capability will kick in. That's kind of our pump storage, other sort of generators that are online, but they're not that fast to respond. You can get a lot more energy out of them over 10 minutes, and they're able to then try and restore the previous reserves. One of the most important things for 10 minutes is to make sure that you are able to restore the regulating and instantaneous reserve, so in case there's a second event, or even, at the worst cases, a third event, because every time you're always trying to restore the reserves. As David mentioned, there is the issue, like for example, when we do load shedding, we don't do load shedding on the fly. We don't wait for this kind of event to take place. You have to plan for load shedding to a large extent to make sure that we know we're going to be short of capacity. Rather load shed, ensure that we keep the reserves available. So, load shedding is never triggered an event like this. This is usually, we have reserves available, reserves are kept whole, so that when something like this happens, we have the reserves available to be able to meet whatever event it is. So that is why sometimes we'll do load shedding, even when it isn't at its max, the optimal point, just because you're trying to keep the system back in balance. I think importantly, yes, sorry, Jessie.
Pause for 1 second, because Isabel Fick is here, and she's got to leave at 3, and she just wants to explain a little bit about national control. Sorry to cut you off.
Yeah, okay, cool, no problem. Go for it, Isabel.
That's all right, for 5 minutes. So Isabel is actually the GM of system operations in Eskom. So she wanted to come in and respond to Louise's question, but she's got a dash at 3. So I think we're just going to quickly do a little smoosh to her and then come back to you, if that's okay. Isabel, can you come in?
I can. Can you see the video? Is that hi Louise. No, I was just smiling when you were talking about, are there actually people there that have to deal with this all the time? So I thought maybe just because there's a broader audience, to maybe just come in quickly. Yes, we have a number of control rooms. My main control room is mostly in control of the transmission network. From there, we have 6 different distribution control rooms where they look after the distribution network and some of the outages on our behalf. We also have backup controls centers, whereby should anything happen in the main control center, we're able to switch over seamlessly to the other one. We tested this very successful. Well, we regularly tested, but during the COVID period, we had to do that a few times when we had illness in the control room itself. So the guys are there 24/7. How many people? 6 people at a time is controlling national network. That's also a question I get a lot. Very well experienced people. At the moment, we've got 5 shifts, and out of the 5 shifts, 3 of them have heads of shift, or as we call them, power system managers, with more than 40 years of experience on the desk. And so actually we have a very competent and very experienced team. I love to talk about them, as you can see. We also have a telecommunications network with its own control rooms and backup control centers as well, to support the national electricity grid, because obviously you cannot control the grid without the telecommunication network. I hope that answers you.
That does. Thank you, Isabel. Thanks for jumping in quickly before you dash.
Please, I'm so sorry I jumped into your presentation. My apologies.
No problem, Isabel.
Keith, so thank you. So if you could carry on where you were, that would be great.
Okay.
There was one question though, which is very pertinent, I think, so it's a point of information. We've got a question just saying that these generators that get triggered, which ones are they? Is it the diesel? Is it the gas? Is it the coal? How does that work? And what is this instantaneous reserve, basically?
Okay, cool, great, perfect. Thanks. Thanks for kind of bringing us back to the technical thing. So instantaneous reserve is predominantly, particularly when we're dealing with the coal power stations. So the coal power stations predominantly provide instantaneous reserve, and that is the ability to increase the steam generation or reduce steam generation by a governor on site in the turbine. So essentially, you're actually just ramping up a little bit of extra power that you can get by pushing through more steam. So the governors themselves, they're installed as part of the process to when you build the plant. But obviously that is a little bit of an efficiency loss. So it's built into the cost of building these power stations that you have this little governor capability, which can provide more or less steam for at the coal power station. Diesel at this stage, I mean, diesel, once it's running, if you've got a diesel generator running or a gas plant when it's running, they can provide regulating reserve and theoretically would be able to do instantaneous while they're running, same way as a coal plant. But usually, we don't have the diesel running 24 hours, well, sometimes, but we try not to. And so the idea is that generally instantaneous reserve tends to be limited to the coal power stations, and they've got the governors to allow us to do that. What we have done quite successfully over the last 10 years is to actually put a lot of this, the burden, should we say, of the instantaneous reserve on consumers. So we have smelters who participate in this program, and that means that they also have a relay on site, which interrupts them. So it means that if you've got a smelter which has a certain thermal requirement, it's able to interrupt for, again, very short spaces of time, up to about 10 seconds, maybe sometimes more, but without having a huge impact on their thermal capability. So they can interrupt, reconnect, and not having had a significant loss of production. That is the bulk of our instantaneous reserve at the moment, mainly because we've had problems with our own generators, ensuring that we can meet the instantaneous requirement, but traditionally it has been on the coal power stations. When we have the pump storage and the diesel running, when they're up and running, they can provide regulating very comfortably. Again, it's that ability to respond to an instruction, and they can then provide a little bit extra power or reduce. What it sometimes means is that those regulating providers are actually outside their optimal position. And here I'm coming into sort of the economics of it, is that if you had, let's say, a pump storage facility, it can do 250 megawatts, and that would be its optimal because of the price of the energy component. What you sometimes do is you put it back by 25, 30, 40 megawatts so that it can move up and down. Otherwise, if it was sitting at 250, it wouldn't give you any additional power. So there's a loss of efficiency, a loss of sort of your optimal outcome, but you need that in order to provide that reactive capability, the AGC capability on the day. So that means that sometimes we move away from our optimal position because the system as a whole needs to be protected. When we get to 10-minute reserve, I didn't really spend a lot of time 10-minute, that's the pump storage generally, and if there's additional ramping that can be provided over 10 minutes from some of our coal plant, that falls under the 10-minute capability. We have an emergency capability, which is really the gas turbines, so the diesel generators. And they have the capability to be able to run for extended a period of time, but they take between 20 to 30 minutes to start up. So they can't respond often when there's an event on the system. They would take a little bit of time to be able to pick up. So you use your other reserves, bring up the gas turbines, and then try and restore the other reserves so it's there for the second event. I hope that kind of provides some of that sort of technical background of what happens with these different types of reserves. Interestingly enough, one of the things that's becoming a bit more of an issue for us, and it's relatively new, is the risk on the upside. We talk a lot, and David showed it as well, that traditionally we worried about the drop in frequency. Now with renewables, you have the other problem where you often can have too much generation, so your frequency climbs. And that can happen when the wind is there when you didn't expect it to, and you can't back off enough generators, you start seeing frequency increase. One of the problems of load shedding is that, as you would have seen, in a local community, you are in and out every 2 hours, sometimes 4 hours at the worst. So, and what that means is that from a control room point of view, and this is where Isabel could have told us more about that, every time we get to the change of in a schedule, when we're going from at 12 o'clock, some units will be, some neighborhoods will be coming back, some generators and large power users, and others will be going off. And that switchover is one of the most fraught and difficult ones in the control room because the frequency moves. I mean, particularly if you're doing 4,000 megawatts under stage 4 or higher, that 4,000 megawatts, you've got to be very careful to make sure that it's moving in steps, because those swings can be incredibly difficult. So that's monitoring frequency on the upside and on the downside, and trying to keep that in balance is also a huge difficulty. With a little bit of time left, I just wanted to talk a little bit around capacity, because I think this would be one of the things that we discuss into the future, is around the backup or the capability to meet demand when there is demand. We have a huge number of generators being developed now, particularly on the renewable front, which is going to be the cheapest energy form of production. We have lots of wind and PV. They really are going to be very competitive from an energy only perspective. But then there's that issue of trying to match the energy production with the energy demand. And how do we do that effectively? And this is where, relatively recently, you start valuing capacity itself as a product or as a service, something that you have to trade and deal with from an economics perspective, separate from the actual delivery. It's always been there, but often we've bundled it together into the energy price, and now you actually have to seriously consider that you start separating that out and dealing with capacity separately. And this capacity doesn't have to be necessarily dispatchable, although it's an ideal. But often, if you look at, for example, some of the capacity markets in Europe and North America in particular, you do allow that renewables are a capacity. They may be derated. For example, wind might be derated by a capacity factor, but it contributes to capacity. It's not that it's just not there. It is. It's just not dispatchable in the traditional sense. And it's a matter of how do we value that the same way that you would value a gas turbine or a battery or other kind of backup capability that we would need on the system. And then just something obviously everyone's talking about at the moment is how do we deal with the network? Everything that I've dealt with thus far, you're looking at from a system-wide point of view, balancing the system, ensuring we dispatch accordingly, etc. But also then when you come to the network, how do you make sure that we are catering for network efficiency? David did talk about the issue of adequacy on the network. It's a huge talking point right now. What it means is that day ahead and in real time, understanding those constraints and making sure that we're able to account for them. It might mean in a future market environment that you separate out pricing areas. You do locational marginal pricing or counter trading. These are all discussion points about when you have a market, how you deal with it. Within the utility, it's still an issue, particularly when some of those suppliers are commercial entities that are supplying into a market. They are actually in a market, but now you, as the network owner, are interfering in that market, and it requires a lot of thought about how we manage that. Thanks, Jesse. I kind of tried to catch up a little bit there at the end, but hopefully we've covered the overview, and back to you. Thanks.
No, that was amazing, and there's no need to catch up time because we've got 50 minutes to go and lots of questions like coming in the chat like crazy. So thank you Keith, thank you Isabel, thank you David for such good inputs. I've been collecting a few questions. I mean, David, if you want to come in and answer them all. Some have been answered live, but I think there were actually two that were kind of the similar topic, which just said, are our generators synchronous? What does that mean for this future challenge of inertia? You guys have touched on it, but if you could just talk it through a little bit again. And then a linked question was somebody saying, will there be enough synthetic inertia? So for people who aren't experts, the synthetic just means not from these traditional generators provided by battery energy storage. Can that replace the inertia from these traditional generators? And what's your guys' views on that and the kind of global trends?
Thanks, Jesse. So I'll take the first one. The exciting bit here is that we have a platform at UCT, synchronize multiple generators. So as a matter of power system operation, when you have two or more generators, they have to be synchronized. Otherwise, one may end up acting as a load and the other a generator. So for both of them to work in sync together, they have to be synchronized. So in principle, all generators are synchronized. Not all generators participate in frequency control, as my colleague Keith mentioned. There are specific generators tasked with frequency response based on their group primary frequency control characteristics. So I think that highlights that. And then there was a question around will battery energy storage be sufficient to supplement the reduction of natural inertia? The answer to that is yes or no, and I'll tell you why. It is strictly dependent on the specifics of the network in question. So let me put a scenario to you. And Keith can speak a lot more about the market aspect of this. But batteries don't come cheap. We'd have to always weigh what is available in terms of financial resources to provide. If financial resources were not a constraint, the flat answer is yes, batteries can provide all the inertia we need to mitigate contingencies, but we don't have that endless amount of resource. So within reason, we can mitigate some of these, but the cost is high.
So I think this is really critical, and that both the presentations have done this really well, that there's technical elements to these questions, but there are also economic questions. And the complicated thing about being an electricity utility or the transmission system operator is that you have to manage both of these complex optimization problems. One question linked to this that's come up twice is, I wonder, Keith, maybe you can respond. What are the typical transmission and distribution losses for South Africa? I don't know if you have that to hand.
Yes, so again, a lot depends on what you want to define under losses, because we have this lovely euphemism, particularly in the distribution space, what we call non-technical losses, which is basically energy that was metered on one end of the distribution network and not metered on the other. That's kind of comes from meters not being in place or having been tampered with. But on the whole, from an Eskom distribution perspective, we look at a target between 9.5% to 10% losses on the distribution network. On the transmission network, it used to be sort of 3.5%, but as we've added renewable capacity into the sort of Western, Northern, and Eastern Cape, that's now dropped to about 2.3%, 2.4% losses on the transmission network. So yeah, overall 2.5%, just short of 2.5% for transmission and 9.5% for distribution.
And that's because those renewables are closer to a load center, so they're traveling.
Exactly.
It has to be this far. Okay.
Yeah.
And so of course distributed renewables would also have this effect, right? With more PV in outside, close to cities, close to load. Okay.
Yeah. So one of the important things, particularly on the transmission network, you've seen the change because of the way in which the energy moves, but it has led to higher losses in the distribution network because of the current, where you actually have a lot of additional generation taking place in rural areas and then traveling across distribution networks at 132 kV or less, which means higher losses in the distribution network. But yes, the closer you are to the load, theoretically, you should see a reduction in losses.
Jesse, just to add to what Keith just mentioned here, one of the complications coming on board here is that at distribution level, we don't have what we enjoy at transmission, which is pseudo-equal power injection across all the phases. And what I mean is, as an example, if you look at your residential area, you have various aspects of that neighborhood connected to various phases, and you have residential homeowners with PV. Some have the capacity to inject into the grid, some don't. So all of that dynamic operation at distribution level, brings about complication for thermal limits for transformers that were designed for a specific operational environment. Now you have a lot more generation happening across various phases, but these complications have been met happily by research and development.
Okay, thanks, David. Our colleague Sunetra's got her hands up. Sunetra, do you want to ask a question?
Thank you very much, Jesse. So just to introduce myself, that I'm a part of the team and working with Jesse and colleagues from the PCC in arranging this webinar and the forthcoming event. And I'm Sunetra Chaudhary. I'm from UCT Electrical Engineering, and I'm the research chair in Energy and Power Systems Modeling. So I think that I'm very happy to see Professor Peter Crossley attending this event, and he was my mentor when I did my postdoctoral research in University of Manchester. So thank you, Peter, very much for joining. So Peter raised a question that South Africa now has higher per capita CO2 emissions than the UK or most EU countries. When will South Africa become net zero? And then there's another follow-up questions from Mr. Mpo Lenswe. what are SS targets in meeting the 1.5 degrees Celsius scenario? So I think that these are all important things, but if some discussion, maybe brief, can be kicked off here from our speakers. Thank you.
Yeah, I mean, Keith and David, do you want to jump in? I mean, part of the rationale for this whole discussion is, of course, that we want to understand these technical complexities as we move towards lower carbon, low emitting, and eventually net zero society. But I think Keith and David can probably jump in and talk about that a bit.
Yeah, I mean,
I'm gonna go mini, mo.
Yeah.
Go for it, Keith.
Okay. Yeah, I think, obviously this is where, as Jesse was saying, the idea is that you look at what are the capabilities in terms of where we are with technology, what is feasible. And I think this is the issue, is that where we are with certain technology is that, you can get close. I'm not sure about 100. That's where we would have to look at about how do you get to net zero, and what does net zero mean? Because you may well still require things like gas backup or something, and then you have to deal with offsets, and what does that mean? I'm not sure yet that we're at the technology which can say that everything can be renewables plus storage. It's just something that we would have to have that discussion to look at the costs of it and the technology. But it's moved on a lot in the time that I've been involved with planning. That technology keeps moving. Who's not to say that in 5 years' time it's totally feasible? But it's one of those things where you have to keep abreast of the technology capability versus what is feasible from the economic perspective as well.
So I want to jump in quickly and say that this is a good moment to tell everyone who's still online and listening that we are having next week an event kind of to answer this exact question, and I'll put the link in the chat for everyone, but we've invited the system operators from a whole lot of different countries, including countries who have got 100% clean energy or 100% renewable targets for their power systems, to talk about, one, the things that they've learned when they've been going from where South Africa is now, so we're at 6% renewables, to where they are now, and they range from systems that are at 30% or 60% and sometimes higher, sometimes much, much higher, and how they're approaching this exact problem of technical and economic feasibility as they go to that 100%. So we'll put the registration link in the chat for people who can come and listen, and we'll have Australia and Denmark and Ireland and National Grid ESO. So Gail had commented about the coal transition that happened in the UK, and how that you can ask system operators from all around the world some of these questions about what they're learning.
Thank you, Keith. Thanks, Jesse and David.
Jesse, there was a question that I picked up earlier on, which was, I wrote it here. So one of the attendees today, I missed your explanation on the relationship between variability versus system adequacy, including how this could be planned for in the long term, interventions required from a technological perspective, and associated investments. Keith mentioned that as well, that within the transmission infrastructure, the concept of adequacy really speaks to, do we have the required infrastructure? And so to be more specific, we have key transmission corridors out of the Northern Cape. When they were designed, concepts and factors such as the surge impedance loading, thermal loading, expected load, expected power flow against reactive power compensation where required, were all put into consideration, and that infrastructure was laid. As we have more power required to be evacuated out of that region, the question is, do we have the transmission infrastructure to meet that? And what's the planning horizon to upgrade that if the rands in the pocket allow for that? So that is the concept of system adequacy in that regard. And the variability there speaks to at the source where PV power has been generated. Solar irradiation is a critical component of this generation, which has its own profile. Literally, a massive cloud cover can shut 80% of your power generation out at an instant, as an example. So what then happens to the load that depends on that power being generated? So I hope that addresses that question. And the question on primary, secondary, and tertiary control, Keith addressed that adequately. I think those are the ones that I took note of. I'll look through the rest.
Thanks. So one that I think is kind of interesting is, given that there's a generation shortage, and I think some of these questions are covering each other, so we may have to come back to them, but we can do that. Well, first, Keith, I mean, please come in on that previous question if you want to, but one of the questions is, why is Eskom not importing more from SAP? So for people who don't know, that's the South African power pool. That's all the countries who together share a power pool. And the question is just asking, why don't they import more from that day-ahead market instead of running on diesel turbines? And I think this will come back to that network adequacy question, maybe.
Yeah, I mean, you're absolutely right. To some extent, it is about network adequacy, but it's also about the fact that there isn't that much additional energy available unless you're going to invest in new capacity. So we have an area called the international trader in the transmission space that goes out, and they've been actively mandated to go out and procure as much as they can in the day-ahead markets, etc. And where feasible, they are doing so because we do want to offset the cost of burning diesel, which is incredibly high. But there is a limit to what's available. And again, it is dependent on water flows and other issues that are happening across the border. But there's a lot of interest, and we are interested in the options of building new capacity, which is capacity that's not there, but we're interested in buying that. So yeah, there are options. Again, for all of these, there's a difference between what's available in the day-ahead market and buying on the short term, and what requires significant long-term commitment. And I think you always have to differentiate that. I see Vickers has posted this thing about the 100 megawatts. That's not day ahead. That's not available day ahead because it's gas turbine. I mean, it's gas produced. You have to be able to commit to a certain amount of offtake for that, and it is definitely higher than normally higher cost than what's available on the day ahead. So we are looking at that. There is a program being run by the international trader to be able to get that, but it does sometimes some of that stuff will require sort of 5-year commitment to ensure. It's a similar, dare I bring it up, the car power ships, that you need to have some sort of sunk commitment to buy that energy over a long period of time. And the question always is, how long do we need it for? Do we need it for 3 years? Do we need it for 5 years? Do we need it for 10 years? And those kind of commitments are quite tricky in that kind of level.
Just to add to the context there, just in case some of our attendees are not aware, the last time I checked, the national demand in Namibia, just across the Orange River, is less than one of Koeberg's units. So when we talk about the trading, we should just remember that historically, Eskom has been the biggest power player on the continent, and I think it still is. Based on the stats I checked, the last time, I think 65% of the power generated on the continent was managed by Eskom. So we are in this predicament. The reality is that building new capacities is the way forward, as Keith has mentioned, and there's a limited amount of reliance that is practically possible, of course, subject to medium to long-term, power purchase agreements with our neighbors.
I mean, this is a really interesting and critical question. I think the IEA Africa Energy Outlook, which looks at, one, how do you meet the SDGs? How do you do energy access? How do you, have industrial development across the whole continent? It reckons we need almost 300 gigawatts of renewables built in across the continent by 2030. We're at 50 gigawatts now. So, I mean, this challenge that we're talking about is actually for all the countries. And one of these interesting questions, I think, will be, how do we start to interconnect and everything? So we've got two questions. They're they kind of overlap, but they're not exactly the same. But one is what's the connection between centralized generation and building lots of grid versus having a lot of distributed renewable energy generation? So, does that Does it mean we will need less grid expansion if we do that? And then Melissa Faries asked, kind of linked to that, you know, how does these geographical aspects of generation matter for the power system? You know, does it actually matter where the power is generated? I don't know who wants to start with those.
I can start. I think for the first one around grid expansion, I mean, we're seeing the problem now where, you know, grid investment has to keep up with the sort of movement in terms of where the new capacity is being developed. And that requires, you know, there's a lot of debate that we can have on it, but it also does require that your funding of the network expansion is there to ensure that it's taking place. I think one of the big things about decentralized is that, you know, there's a lot of benefits to decentralized grid, decentralized generation, but it's also ensuring that we deal with the diversity nature that is already inherent inside a distribution network. When you're looking at low voltage, you know, you build in a certain amount of diversity when you kind of planning for it, that not all consumers take their maximum energy at the same time. It just doesn't work that way. So you can, you know, let's say cut corners, but it's more efficient that you don't have to expand the transformer to the maximum it needs to be in order to meet everybody at exactly the same time. That doesn't always work when it happens in reverse. It's basically that, you know, if there's solar and it's PV on the rooftops and everybody's got it, you're going to have that problem where it's all flowing into the network at the same time. And now you have to counter for the lack of diversity when it was there previously. So it is definitely an issue from the design of networks to handle a lot of that shift. I'm sure David can give a lot more of the technical kind of issues that come with that. I mean, I'm an economist. I like to look at like simple flows, but definitely there's a lot more that goes with that. And that is going to be expensive. There definitely would be benefits, but it also comes with its own costs associated with it.
Absolutely, Keith. And just to add to that, when distribution systems are designed, and this is a philosophy that pretty much most of the utilities around the world use, based on the concept of ADMD, after diversity maximum demand, which speaks to it cannot be reasonably expected that we all draw maximum demand at the same time. And that's literally based on how the physical infrastructure is designed, the wires, the transformers, etc. But then if we have a high number of renewable energy generation at residential level, the sun will hit that area at the same time. And all those installations will generate at the same time. If it's peak working hours and most of the residential homes are not occupied, as an example, then you have these new challenges coming up. In addition to that, we have new challenges around the area of non-uniform injection or power trading on each of the phases. That poses a new challenge that needs to be managed. And the solution lies in modern inverters that will have the capability of managing those situations. I know colleagues in Italy have been working on a few projects around decentralized generation control to mitigate some of these challenges that we are beginning to see in networks around the world. Thank you.
Jesse, can I come in and answer one of the questions about locational marginal pricing? Because I think it's a really important one, particularly in the context of where we are with network constraints, and because we you know, obviously we haven't really talked about it a lot here, but we're in an environment where we're looking at developing a future competitive market and market trading platforms. How you price for network constraints become quite a key issue of how the future market would work. And there are numerous options that you can do for network pricing. Obviously, we separate out between a network pricing from the perspective of how does the network operator get its revenue for operating the network versus how do you price energy that's traded across the network. And here I'm focusing on the energy component. The three main ones that I kind of just to highlight, I talked about the price area possibility, that where you have a constraint, you allow for the bids and offers on either side to clear separately. And so you end up getting a different price zone. And that's how they do it in Europe to a large extent. You have prices in the north of Norway, mid-Norway, South Norway, Denmark separately. And each of those are, because they're bound by technology constraints, the prices will differentiate. The moment those constraints are lifted, it should equalize across them. And it's quite a neat way to be able to see, well, there's a reason for the price difference, and trying to then find out some way to accommodate that. The one problem I have with the price areas is, how do you then move on to the point where you incentivize a network operator to alleviate the constraint? What is the incentive for them? And there's a lot of great theory behind it. I just always find that it's not automatic. You have to have a regulator that's really on the ball, sees the price differences with consumers wanting those price differences to be resolved, and going out and fixing it. The alternative is the North American kind of base model, which is a locational marginal pricing, where at every node on the network, you have a different price, and that would be differentiated again by constraints, but also by losses across the network. And I think that is, it's an option. I always find that, and again, this is me, so it's not, I'm not saying this is right or wrong, that the problem is it leads to a lot of complexity in terms of prices across the network, and everyone has different prices. So you have to start having transmission, financial rights, tradable rights that you kind of now try and equalize again and deal with these differences in order for people to trade easily across the network. So to me, there are issues, but it also comes back to that issue of, how do you incentivize a network operator to fix it? If everyone's just paying for it in the market, and you can turn a blind eye and just say, well, they're happy with it. But then the third option, which is the one I favor, I'm not going to say that's the right or wrong, because it also has huge amounts of issues with it, is the ability to counter trade, so that you have a market clearing where you're kind of ignoring the network. Then you do a security constrained kind of dispatch, and then see what the differences are. And the system operator, network operator, then has to compensate generators up and down, because you've now adjusted that, and then that cost comes to the network operator, and you have to then recover that somehow. And of course, that's where regulation comes into it. So I think it definitely is something that we have to spend a lot of time on. I'm saying I have a bias in terms of, you know, how do you force the network operator to do something about it, but there are many pros and cons to that. I think one of the important things to bear in mind is a lot of the traditional models, particularly in Europe and North America, focus on the transmission grid, and they work well, locational marginal pricing across the transmission network. But the moment you're now going into the distribution network, and the complexity of your solution becomes a lot harder to deal with as you become, more and more nodes into the mix. You may want to think about a different methodology, but it is something to consider. I'm just saying this is kind of fully aware that this is a crucial component of the future market design, and we have to deal with it because it's a reality. Network constraints, particularly in the Northern Cape, Western Cape, going to be an issue for a while, and you have to have mechanisms for it.
Thanks, Keith. There was a short follow-up, and then I think I'm going to go back to some of the more technical questions, because there's quite a diversity, and I want to go back to making sure we covered everything in the presentations. But the follow-up was just like, how will Eskom redispatch costs as a monopoly be addressed beyond transmission constrained prices? I don't know if you want to take that.
Yeah, I think, again, this is think about in terms of, once we've developed the market. So I can give you an answer for now, and because right now we just basically bundle it all into a tariff that everybody sees. But in the market environment, your system operator still is technically a monopoly service. It would be doing redispatch, and it might be doing redispatch because of network constraints or because of system balancing. And both of those you have to account for slightly differently. And I can go into a long technical argument about how you do a sort of out of merit dispatch versus in merit dispatch. But the idea is you still have to, as part of the balancing mechanism, you would charge the people who cause the imbalance. But when it comes to the constraints, and you're using sort of dispatch to fix constraints, then you, to some extent, you'll socialize, and to other extent, you would actually apply to the network operator that they have to recover it as a cost, as opposed to actually investing in the network to ensure that they can alleviate that cost into the future. I hope I answered the question, but again, it is a tricky one. Right now, as a monopoly, it's just added into the sort of the bottom line for everybody. But in the future, you want to separate that out so that everyone can see what the cost is of generating or consuming across a network. Thanks.
Thanks, Keith. This one's for David. David, what is the difference between load and demand?
It's a very good question. In general, load and demand is one and the same thing, depending on the context of use. As an example, if you want to design a backup system for your home, one of the critical elements of that whole process is, what is your load? And the answer to that question is, how much power are you drawing? And what you draw is what your demand is. I hope that answers the question.
Thank you. So there's some sort of similar-ish questions around technology. I mean, what are the technologies we should be considering? What about flow batteries? Like, why hasn't there been so much attention on flow batteries? What is the issue around maybe new nuclear use as a generator? And that kind of gets us into that long-term planning discussion a little bit. Maybe you want to come in on that, Keith or David. I think, yeah, that's great. If you can talk about that, and then yeah, thanks.
Right. So I think just whilst I still have my microphone just unmuted, various countries, governments, and departments, decide what's the best for that country and the network. So that's the fundamental thing that needs to be done, and based on that, technology follows. I hope that answers the question.
Yeah, I think just to add to that, I think a lot of it is also around as Jesse says, the sort of the paradigm in which you're doing the planning. So we're seeing now that from a technology point of view, particularly if we're looking at storage, battery storage, it is all about lithium ion. Everywhere you turn, it's about lithium ion because of the cost, the high cycle efficiency. But when I talked earlier about going to net zero, what's feasible, lithium ion is unlikely to get us there because it is such a short window to be able to supply energy. Talking 4 to 5 hours. Whereas flow batteries, there's a huge benefit there for flow batteries, but then you have to do that trade-off against the efficiency loss, the cycle efficiency loss, and the cost. But it might be that flow batteries, technology change may lead that flow batteries become more feasible. But right now, if you're left to the market to an extent, everyone just goes off to lithium ion. And that, I think, is part of the discussion we have to have about the technology going into the future. I think nuclear, again, it's one of those things about if again, purely from a technical perspective, nuclear is always there. It's kind of, there's a base load capability. It provides for energy at a sort of I'm not going to call it dispatchable because it's not always dispatchable, but it provided a more predictable format. But I think the big problem with nuclear, and everyone has to consider this, in an environment where you have huge amount of flexibility from other sources, and particularly the wind, the solar, etc., nuclear would probably be one of the worst options to deal with that sort of flexibility, purely from an economic perspective, that you spend a huge amount of money to build something and then underutilize it. If you build nuclear and you use it 100%, fab, you get a good outcome. But if you build nuclear and then you have to run it at 70% or 60% or even lower, because now your trade-off is curtailing wind and solar and running my nuclear, or allowing the wind and solar to run and then curtailing my nuclear. And both of them really are, you start moving into a suboptimal kind of outcome. So it becomes an economic question more than a technical one, because technically it's feasible. Particularly nowadays, nuclear is dispatchable. But would you want to? Because you spent a lot of money on something which you're now going to underutilize. So that to me is always the debate that we should have on nuclear, and it's not about rights and wrongs, but purely about the economics. Thanks.
David, I'm not sure if you want to add anything on that.
I think it's been well elucidated, so I'm quite happy with his response. Thank you.
Okay, that's perfect. So here's a question from Steve. He says, what's your view of the existing feasible penetrations of variable renewable energy globally? I mean, globally is a hard one. And then also if you could comment on where there is these kind of long-term analyses of the South African power system, are there very large differences in those kinds of levels of penetration in the literature?
Yeah, I mean, again, I can take a stab and David can correct me if I've got it wrong. The big thing is that when you look at the global information on this, a lot of the time, those areas where you can do high penetration tend to be interconnected with others where that penetration is not so high. So their huge amount of wind and solar that can meet their demand at a protected time, and I'm looking at Scotland, Denmark, and those sort of countries, it looks great, but they are always able to depend on a neighbor that can actually supply when the wind's not blowing and the sun's not shining. So it really is a reality of what is feasible. I think the best is to look at places like Hawaii and those sort of places where it is isolated. You have to meet your full demand. It has been done, but then it's about scale, and can you actually execute that for 40, 50,000 megawatts kind of peak demand, and what does that mean from the kind of options that you would make? So yeah, I think the whole thing is you've always got to look at the context in which you're actually measuring that. And the reality right now is that, we are to a large extent isolated. And I think it's important to be able to identify that.
Yeah, I think Keith's question response was spot on. If you look at our European counterparts, Germany, Austria, France, Italy, if you drive around these countries, you will see how significantly small they are compared to South Africa. That also speaks to the size of the network physically. The load is something else. And the high level of interconnection and dependability between neighboring countries. As I've mentioned earlier on, in the SAPP, Southern African Power Pool, Eskom is the largest player, and by a far stretch compared to the others. So within the concept of power system reliability, it is not only about having a high level of renewable energy penetration, but to be secure and adequate. Those are two critical elements that will guide that decision-making process.
Yeah, so I mean, I think we've got quite high agreement in the long-term models on this issue, right? South Africa's got a lot of modeling capability, and we can put some links in the chat for people who are interested to see kind of where those economic levels are, and it's usually over 80% consistently across all the groups that are doing that kind of long-term planning. Also, to again make a pitch of our event next week, we've specifically invited systems that are similar to South Africa's in as much as we could. For example, islands like the United Kingdom, or systems that don't have a lot of interconnectors, or where they don't have a lot of hydro, because to try and say, of course, context matters, but where are there some similarities? So in what ways is Australia facing similar challenges to South Africa? So everyone must join there and ask the system operators those questions. Okay, so we've got a lot of questions on more policy questions. So I'm going to try and focus a little bit on these technical ones, because we've got these technical geniuses here specifically for this, rather than some of the more kind of not non-technical ones. Melissa's asked, what are the consequences of much having far lower maintenance requirements for renewables for that power system? So, is it better for the system if you don't have to respond to the loss of large units for maintenance like we do with coal and nuclear? Kind of how does that play out? And then I think if you can think of a little bit for the next one, a little bit kind of what's the role of electrification of end users? I mean, the specific question is around electric vehicles on the demand side, but I think it's a kind of bigger question around the demand side and electrifying end users, and how does that interface with the grid and the system that we have and that we're going towards?
Right. In terms of faults, large power stations compared to renewable energy installations, from my perspective, an electrical installation, or any in fact, have certain properties, which is the potential to fail at any point in time. This is carefully calculated in the design process and aging and planned maintenance. So be it a solar plant or Koeberg, the nuclear power station, failure is still a possibility, but this can be carefully managed and calculated based on the design of each of the various components. So it is still possible for you to have a 50 megawatt PV plant that can go offline if there's a major fault. Keith?
Yeah, I'm just agreeing with you, particularly if you consider that often, even with a renewable plant, yes, there's a certain amount of reducing risk because you have, 5 turbines instead of, 1 or whatever. But so often there are common mode failures. I mean, we have one IPP right now that has been off for a number of months because of a transformer issue. So it's a single mode failure that can affect a renewable IPP just as much as a coal or anybody else, But to some extent, the more you diversify and you have numerous suppliers, then you can actually spread that risk a little bit more. And I think that really is maybe the issue is that, you have big power stations with, big capability. By having multiple smaller ones, which previously was not efficient. Having a whole lot of small coal power stations is just not efficient versus having one big one. But maybe with wind and PV, you can get the efficiency losses not as severe, and then you can spread the risk a little bit more. But there's still that when you have, like, for example, a farm, a wind farm or a solar farm or whatever, and they connect to the network through a single mode failure, it can be pretty hectic. We've seen it with CSP plant, concentrated solar. Again, all that energy, all that heat is going through a single turbine. When that fails, it's all for nothing for a fair amount of time. So those are the risks. But I do believe that as you can get more and more suppliers and you can be more modular, you're not depending on large single failures as we do right now.
I mean, this is maybe another key takeaway, right? Like, what we really worried about is the system and the way keeping it in balance at every moment of every day of every sub-second for the next 150 years and longer, and having these trade-offs and kind of optimization challenges is really what it's about. Sorry, Melissa says her question was actually about maintenance, not failures.
Yes, so just expanding our response to maintenance. Yes, rotating parts do have generally a higher degree of maintenance requirements compared to machines without rotating parts. So if you have a 100 megawatt coal-fired plant and a 1 megawatt PV plant, it is almost certain that the PV plant would have lower maintenance requirements compared to the coal-fired plant. So that is a response to that.
Yeah, I think one of the other benefits also when you have a farm, so a wind farm or a solar, is that often the maintenance can be circulated within the farm, and we just don't see it. We see it all the time with renewable IPP generators. You don't even know that, instead of giving 100 megawatts, they're giving 95 because they're circulating maintenance, and it's not a big impact because the plant itself can function. Whereas obviously the larger the power station, the more that there's a 600 megawatt generator out, and it's kind of evident. So yeah, I think there is some benefit to that, that you can keep the whole facility operating while smaller components are being maintained.
And I suppose you don't lose big chunks of power in that way.
Exactly. Yeah.
Okay, here's an interesting one. I don't know. In the next decade or so, there'll be more days that are hotter than 40 or 45 degrees, more droughts, etc. What's the implication of climate change and variability for thermal plants? Is this being factored into planning?
Yeah, from a planning perspective, I can't actually say what's been factored in. I think it definitely is an issue. We know that at coal power stations, ambient temperature is a massive issue, and that as we get hotter and hotter, those losses become higher, the risk of failure become higher. But it then could also theoretically can work for solar PV, that as it gets hotter, PV also goes outside its normal range of operation, and you start having losses. So it definitely is an issue that climate change has a massive impact on the ability to deliver. I think work still has to be done is what does it mean for wind if it's hotter and maybe the winds could be blowing more, but what if it's blowing less, and what does that mean in terms of production as well?
David, I'm not sure if you want to come in on anything related to that.
I think it's sufficient. Thank you.
Okay, so Abraham had asked us earlier, how does the system with renewables cope with riding through major faults? And I think it's something that both of you spoke to a little bit in your talk, but it might be worth giving another short discussion around that if you don't mind. David, maybe you can take that one.
Yeah, sure. I'll take it, and I will go back to that figure that I had earlier on. So when at the point of a contingency, an example would be a large loss of load or the coming online of a large a large power station such as Coburg Unit 1 or 2. If you at that instant, if you have a significantly higher level of load compared to generation, you will have an under frequency situation. Typically, the governors at the power stations participating in primary frequency control, as Keith mentioned earlier on, will respond to try to balance out the frequency deficit. And then secondary and tertiary frequency control kicks in. Of course, tertiary moves into economic dispatch, which is a slightly longer horizon. These dynamic nature of synchronous machines is defined around the inertia of the synchronous machine, is what allows for that relatively quick ramp up, ramp down. However, in the power system with a high level of converter interface generation, and what I mean by that is, as an example, PV-based power generation, it all depends on what the reserve production is compared to the committed level of production. And generally, from an IPP perspective, you push it all you generate. Okay, that's the financial model. Keith can correct me there. So it is more of a challenge to use converter interface generation to do that. But technically, it is possible to ensure that we have that reserve, possibly in battery energy storage, to mitigate that. The second point linked to this is that because we have a higher level of variability, we have a higher possibility of frequency excursions out of bound, which places a higher requirement on primary frequency control. So I hope that answers the question.
Yeah, Keith, I don't know if you want to add anything about the market design as well around what other plants in the system may or may not be asked to do, or they kind of how they might be asked to operate to address this challenge.
So there are a couple of things, particularly in the provision of reserves. And I'm not going to look at the other ancillary services. I know there was a question just now about synchronous condenser operation. I mean, that SCOs, synchronous condenser operator or generators, really work well for reactive power and ensuring that we have that voltage support and reactive power. And there's an ancillary services specifically designed around ensuring the ability to manage reactive power and voltage support. But when it comes to reserves, and again, there are a couple of items that need to be addressed. One is loss of opportunity. So as I was mentioning, sometimes the system operator is going to need to use very fast response kind of generators, those that can respond quickly, but they're not, they might have a more optimal energy solution. They might be like, let's take a battery, for example. The battery, it charges at 50 cents a kilowatt hour or lower in the middle of the night, and now wants to run at 5 Rand a kilowatt hour to offset diesel. The system operator says, no, sorry for you, but I need you for very fast response, and holds it in reserve. That's a lost opportunity. That battery could have made money. It needs to recover lost opportunity. So that's one of the market designs, is looking at that lost opportunity, ensuring that the people who are providing reserves are at least better off providing that the reserve than they would have been beforehand. But there's also the capacity, the capability to provide that fast response, which can be expensive. So you pay for capacity as a service, and you may pay a premium on that capacity to offer fast response kind of service. So these are all sort of market design elements that look at one, loss of profit kind of capability, the optimal position, paying for capacity, just for being there, but also for the response and the fast response, which must come at a premium. So that would be a key component of that. I think there's also A couple of questions there, if I can just quickly ask, because Rabacholo had put in a couple there about CCGT capacity factor. I think that's an important one. Right now, we would run CCGT if it were available, 90 to 100% because, we're load shedding. But in 2 years' time, it may come down to mid-merit. 2 years after that might be a peaking issue because now it's more about the support for a renewable heavy generating fleet. And you're there to just make sure that we're able to meet demand when it's there. So it's difficult to say what is, but realistically, the way when we did design for the stuff 10 years ago, you looked at sort of between 20 and 60% kind of load factor. Any more than that, you're kind of really looking into the base load realm, and maybe other things could provide that. But less than 20% it's possible because now you're focusing as a peaking. You wouldn't use CCGT, you would use OCGT instead. But a lot of the modeling at the time, we looked at both, that you want OCGT and CCGT. Maybe if we're looking at 5 years hence, we might only be looking at OCGT. Maybe there's a limited window for the CCGT, but it's a discussion worth having. And I think just the one about the costs, I think it is definitely around the issue of, one of the colleagues I worked with said that if you went and did a survey of everybody who worked in sort of generation planning, and you looked at people when they started, and when they've, where they are as 40 years after having done it for 40 years, you'd get a nice curve that everybody in the beginning says everything's fixed. And as they get older and older, they realize actually it's not so much fixed, it's more variable. I can't remember, I might have got it the wrong way around, but it's just interesting that everyone has a different view. So what's the percentage of fixed to our cost versus variable? But the reality is, as we get closer and closer into sort of real time or day ahead kind of modeling, it all becomes a lot more fixed. We kind of lose that variability. But up front, if you're making a decision about tomorrow, then everything is variable. So right now, if I listen to my generation colleagues, I would say that we're looking at 60 to 65% fixed and only 30% variable, because it depends on what you do with the fuel. A lot of the fuel is in long-term contracts. We spent the money, then whatever we're buying is only a small portion above that. So then, we have very little options. So it then becomes very fixed. But other people might tell you have a lot of flexibility. We've just locked ourselves into those contracts over time. Thanks.
Yeah, it's a critical question, right? As you maybe run the coal plants less or use them more as peakers. David, could you maybe take this question? Are grids, so are the wires better with overground or underground cables? And I'm thinking about the California wildfires. I'm sure that's what Rexford is thinking too. What are the benefits or costs of those two options?
Thanks. Good question. It depends on if we're talking about high voltage, extremely high voltage transmission and distribution, and just between houses. So for high voltage, there are thermal considerations that makes it a preferred option to have overhead transmission lines. Within the neighborhood, residential, commercial area, from an aesthetic perspective, it makes sense to have underground cables, though they do cost a bit due to the thermal considerations in their loading capability. So it depends on the specific environment that you operate in. But from a technical perspective, our overhead transmission lines at high voltage allow a lot more power to go in through these lines per unit cost compared to cables. Just as out of interest, between I think the island of Gotland and I think is it Finland or Scotland, the first underground, underwater high voltage DC transmission link was installed in the 1950s. The obstacle there was they needed to connect mainland to the island, and there was water, and they had to do that via underground cables. In Italy, there's an island called Cagliari on the south coast. It does have some high voltage DC transmission to mainland. Interestingly, Cagliari has a high level of PV-based power generation. So it depends technically on the context and the environment.
Thank you. And Dudu Khadebe, who's from Eskom, has just also very kindly said fault detection and maintenance is more difficult with underground cables. So that's also another thing. Finding the problem is going to be more difficult. Thanks everyone. We're actually out of time. I'm really sorry there are a few outstanding questions, but I think they're less technical, so I don't feel so bad that we've not answered every single one. Thank you so much to our speakers. I'm sure that if people still have outstanding questions around how power systems are operated, what is this system for, how does it work, that they can drop an email to us and we'll try and get you a nice answer. I just want to say, wow, like, thank you for your time and your expertise to David and Keith. It's been absolutely amazing. Thank you for all the really good questions from our listeners and the comments have been super. We've covered a lot of ground. So we've gone all the way from the basics of power systems. What are these concepts like security and reliability? Why they're so critical for system operators? We've seen how important planning is for secure and reliable grids. We've seen how technology intersects with economics. Again, please everybody sign up for the event next week. And thank you very much, of course, to our funders, the Australian High Commission in South Africa, because that's what's letting us have these events and bring overseas experts and have overseas experts dial in to talk through all of their systems. So thank you very much. And like big round of applause virtually for Keith and David, who've been absolutely outstanding. Thanks, everybody. Have a good day.
Thanks.
Thank you.
Thank you. Thank you.
Great. Cheers.
Thanks, Jessie. It was great.
Cheers.
Yeah, you guys are amazing.
Thank you.
We just leave now.